Right, thank you. So our next speaker is Marc Huertas. He's going to talk us about morphological influence in diversity in JWST images.
Okay, so apologies for the technical issues. I don't know what happened, but now it works. So very nice to be back, as always. Thank you again to Joe, Lavishai, and all the Santa Cruz gang for keeping organizing this. This is very nice. And I'm happy today to report a little bit on the work we've been doing to understand the diversity of galaxy morphologies. I've been talking about galaxy morphologies for many years here, and now we can talk about galaxy morphologies with the JWST, which is exciting. So Sandy mentioned yesterday that 20 years ago we were wondering already about these questions. And so these are very general questions: how galaxy diversity emerges across cosmic time, and how, when and how the first disks and bulges emerge and are formed, and how quenching and also how star formation and morphology get connected. And I guess, these questions are still open. We have made lots of progress, but, they're still open questions. And I think there's a general consensus from, what we learned from HST. These are plots I showed several years ago here at this conference, in which, we know that the morphologies of star-forming galaxies, this is not working, become more disturbed as we go at high redshift. You can see there that, we have been discussing here at this conference a lot about clumpy galaxies at high redshift, and, star-forming galaxies are disturbed. And we also know that, there's a relation, at least, between morphology and quenching for the last 10 gigayears. So candles has probed up to redshift 3, and we know that, when you look at galaxies, massive galaxies that stop forming stars, they are essentially, bulge-dominated. And of course, JWST can, if we want to, understand when these started to be connected, and, what's the previous, or the first evolution of these systems, you need to go at higher redshift. And of course, HST has some limitations, because as you start, probing higher and higher redshift, you start probing the UV res frame, so you're biased more towards star-forming or, young star-forming regions. And one of the reasons of building JWST was precisely to probe the old stellar populations at high redshift, and now we can do that at even better resolution than HST, following the, infrared filters of JWST. And so, JWST was built, essentially, one of the main reasons to build JWST was to understand morphology or galaxy diversity at high redshift. And this was, of course, a low-hanging fruit. And so when the first data arrived, lots of people jumped into it to look at it. So at the CEERS team, Jehan and all the team led a nice effort to try to, visually classify traditionally galaxies in the first CEERS pointings. And all groups, agreed, and Brand also mentioned it yesterday, that we seem to find that when you go at high redshift, a large fraction of what we call disks. So, and so, what JWST seems to be saying is that, we are seeing more disks or less disturbed than we initially measured with HST at a high redshift. And you see that Jehan measured a fraction of, over 60% at redshift above 3. And so these, of course, are based on visual classification, small data sets. So we try to, when more data arrive, try to understand a bit better what's going on here. And of course, I threw in some machine learning into that, because this is what I do for a living. And so what I tried here is try to get a more systematic, understanding or, characterization of galaxy morphology, now with larger samples. So now 20K galaxies in CEERS. And I'm not entering into details of what we did, but essentially we're trying to classify CEERS galaxies without any labels. So this is just, but reusing some information of what we learned from HST, but trying to, get rid of everything that is specific to HST and just, make the networks learn new things, but without being biased of, the labeling of HST. So not entering into details, but essentially feeding both information and getting rid about instrumental effects. And so this is a general trend in the galaxy morphology business, in which now we're trying to make classifiers that are more and more general enough and that don't depend on specific labeling. And so basically we are able to classify galaxies in several classes, spheroids and bulge-dominated, and these galaxies in multiple filters. And just, this, of course, is not novel. It's become an industry. So just before I go to that, just to mention the power of JWST. So this is, previous classification, previous data set from which we had morphologies in candles, so redshift a function of stellar mass. So we see at redshift 3, basically, you get 10 to the 9 or something like that at most. So this point is here with JWST. So you go much fainter in lower masses and at higher redshifts. So as I was saying, this is not novel, but I think one thing that deep learning or artificial intelligence is bringing to the community is a way of accelerating science. And I was just looking at how long it took to classify more or less 20K galaxies in candles. It took 4 or 5 years essentially to get this done. Now it's a matter of a few months to get a similar sample with similar quality of galaxy morphology. So what we got here, so now we can exactly compare apples to apples and compare HST. Just one little thing I cannot resist. Now Euclid is launched, and so this accelerating of getting classifications of galaxies will have a strong impact on Euclid. And I will do a short break into my talk to talk a little bit about Euclid, because it was launched. It was a very nice birthday present this year. So it was successfully launched, and Euclid is a 1.2 meter telescope European mission. So after talking about JWST, 1.2 meters doesn't look like very impressive, but of course, what Euclid has, so it has near-field coverage, it has optical coverage, but essentially what Euclid has is a tremendous field of view. So these are first data released from first observations from the commissioning of Euclid. So it's now taking data, working nice. And the nice thing about Euclid is that it has a 0.5 square degrees field of view at the HST resolution. So this is, incredibly large. So we're going to get large field of views with, not as deep and with such resolution as JWST, but still quite impressive. And also in the near infrared. So Euclid will do a wide survey, which will be now 15,000 square degrees, and at a depth of 26 in the I band. It will do a deeper survey, which is still non-negligible 53 square degrees, and it's 2 magnitudes deeper. But it also will observe very soon, well-known fields, including candles fields and cosmos fields for calibration. So we'll have overlap on those fields. And so we have been working hard to get morphology measurements for Euclid, and so everything is ready. We will have, so for you to use parametric morphology, so CEERS fits for all Euclid galaxies in the pipeline already measured. And I think it will be the first space mission to have integrated in the pipeline deep learning-based classification based on the work by Mike Wolfsley and that we've been doing in the collaboration. Anyway, so just going back to JWST now. So what we've done, therefore, is getting this classification in the 4 filters up to redshift 6, more or less. And so we can now compare apples to apples, HST and JWST, and see, what are the differences in the terms of morphology we measure. And so so just a hint of, what the classifications look like. So we classified bulge spheroids there. So you see different beams and stellar mass and redshift beams. So bulge and spheroids there, more disky galaxies. These are more irregular or disturbed, and these are bulge-dominated systems, but with some extended structure around them. And so what happens when you look at, for example, redshift 3.6, and we compare, same waveband, so more or less 150 and 160 in HST and JWST, and we compute the fraction of disky and bulgy systems as a function of stellar mass here, and the fraction of disky and irregular systems as a function of stellar mass. And you see that, dashed line is HST, solid line is JWST, so they look extremely similar. Okay? So no much difference there. So why, we're measuring more disks in JWST? The point is that when we change wavelength, and so these are just a comparison here of both. So you can see that, the resolution is much better, but it's impressive that we're getting essentially the same answers. But the key point here is that when we change wavelength, so now we're comparing 160 on candles to 4 micron in JWST, now we see a strong difference there, okay? So now you see that, there's a clear trend with mass here, and then everything was dominated by disturbed systems in HST in 1.6 micron, then you can see that, there's a strong correlation with mass, and at the high mass end, you did see less disturbed systems, more disky systems. So is it true that, this formed earlier than we thought? Eventually, this is what JWST is telling us, at least. But this is not a consequence of spatial resolution, it's more a consequence of wavelength, gate correction, let's say. So now when we put everything together, so these are, now following at the same rest frame band, so 2 micron, 3 micron, 4 micron, the fraction of regular and irregular disks, systems, and bulge-dominated and disk-dominated, you see that you see a smooth transition, similar trends. We get more and more disks as we go towards lower redshifts, but still, even at 3.6, at the high mass end, we see, that there are a significant fraction of disks at the high mass end. And also interesting, the high mass end here is, of course, dominating by bulge-dominated systems. Here, it's not dominated anymore, but we also see the same trend. And, the transition is quite smooth, so it's telling us that, as opposed to what we measure with candles, now the things are smoother when we observe at the same rest frame band. So the key point here, then, is that we get still at these redshifts, we still get bulge-dominated systems, we still get disk-dominated systems, or, regular systems at the high mass end. Another interesting thing is that, what about the connection between morphology and quenching? So this is another way of looking at this, is different redshift beams here, and different stellar masses, and we measure the fraction of, bulge-dominated systems as a function of the distance to the main sequence. And you can see that, when you go at high redshift 3.6, you still see again that, even at these redshifts, when you depart from the main sequence, you're still dominated by bulge-dominated systems. So the trends are extremely similar. So of course you get more and more, but even at these early epochs, quenched galaxies are still compact and bulge-dominated. So the connection really between morphology and quenching happens very early. And by the way, this favors this so-called progenitor bias in the sense that, you don't have time to build a progenitor bias. The time is very short. So if, things are still bulge-dominated, quenched still bulge-dominated, there must be some connection between the morphology and the quenching. Okay, so now going back to this and making the link with what Viraj said yesterday, so we measure that visually these guys are morphologically apart, they look like disks. Are they really pitas? Are they really rotating stellar disks? That's the question. And Viraj already told you some answers to that. So these are the things that we classify as disks, just to get an answer, a feeling of, what are we calling disks. So it's not that obvious from these. And so just recutting what Viraj did, nice work, so trying to understand the 3D shapes of those, and he's finding that, many of these elongated things might not be this pita thing, but more pickles. Thank you. And so what we wanted to go is to do a different approach, trying to get a bit more insight on what is the nature of these systems. And again, I'm going to put in some layer of machine learning into the business. So what we try to is to compare what we get there to the simulations and see if we can get some insight on the nature of these systems. So what we did is, took the PNG cosmological simulation, getting some mock images without any instrumental effects. So just, assuming some M over L and stellar populations, and then adding instrumental effects from JWST. So when you get a nice disks, even at the JWST resolution, when you go at high redshift, you get something like that, which is similar to observations. Okay? And so using the fact that we can get the intrinsic morphology here at high resolution and high signal to noise, we wanted to build a framework, a machine learning framework, that is able, to represent these images here in some space that are robust to these perturbations. So get, something that you can try to recover the information that is here from the noisy version, let's say, and see if we can get some information about, the physical nature of these systems, less biased by pure morphological classifications. So we use something that is called contrastive learning, which is now rebranded as foundation models, which is very fancy name. And so, but the idea is then we fed, at the same time, this noisy, perturbed version of the image, this, high-resolution image, and we try to project this into a manifold here, a high-dimensional manifold in which we want these 2 points to get together. So essentially, when you try to learn some features, extract some features from these images, but are independent of the noise perturbation, say. And so you get that all intrinsic morphologies will lie together in this plane somehow. So I guess this is a bit complicated, but just let me through this. Now, this is a representation of this manifold, and because this is a simulation, you can go back. So every cell here computes average physical properties. So in this manifold, this is the manifold representation of the manifold where these galaxies fall. And now for every position, you can compute the average physical quantity of galaxies lying in this particular position. And this is the stellar angular momentum. And you see that, based on the images now, so things that fall in this region of the manifold have low specific angular momentum, and things that fall in this region of the manifold have higher specific angular momentum. So by, I'm not doing any specific, I'm not plugging any physics, only by plugging the information on the images, I'm getting a natural correlation with physical properties in the simulation. Okay? So now if you drop a galaxy and falls in this region of the parameter space of the manifold, you know that it most likely have a longer specific angular momentum. And also it correlates with a 3D shape, right? So things here are thicker, and then these here are flatter systems as correlated with the angular momentum. Okay? And these are, images stamps of this TNG simulation high resolution, and how, they correlate with this, the shape correlates with the physical properties. So now that you learn this mapping, you can just, throw in observations into this manifold. And now if you throw in JWST galaxies here and look where they lie, you can try to infer, what are more or less the physical properties of these systems based on the image. And of course, with lots of caveats calibrated on the simulation. But, we can try to learn the physical property, one of the properties of these. And what happens if you do that? So this is exactly the same manifold, but now instead of showing average quantities, I'm showing individual galaxies. So gray points here are the simulation, so TNG galaxies. And colored points are observations. Okay? And so, and the different colors are the classification, morphological classification. So again, just to guide your eye, so this region is what I would expect that with low angular momentum systems. Okay? So these are things that are expected to be low angular momentum, not rotating. This region would be things that are, rotating and, flat systems. And you immediately see that, okay, so things that are classified as spheroids or bulge-dominated lie in this region, as I would expect. They are not rotating, they are compact. But, a big fraction of the disks, which are an irregular system, which are these blue things, lie also in this region over here. So low specific angular momentum and not rotating systems, okay? There's a fraction here, but a large fraction over here. So at least 50%. So what does that mean? So maybe they are not disks, or there's something else. So one obvious explanation is that, these are very small systems, and so there's no match between the simulation and the observation. And we need to compare to more simulations, okay? And so it could be that these are simply small disks. They could be disks, but they are not properly resolved in TNG. And actually, if you look at, for example, the mass-size relation and that we measure with TNG at redshift 4, it's much tighter than the scatter you measure in observations. So in CEERS, we measure much smaller disks, systems at high mass than we measure with the simulation. Okay. The other alternative is that they are not disks, and actually, we can measure because we have access to the 3D shape, we can measure where, the 95% contour in this manifold where oblate systems are expected to fall. And you see that in that particular region, at least calibrated from the simulations, there are no flat systems. So everything that lies here isn't expected to be a flat system. So it could be that 50% of the things that we classify as disks, in fact, are not disks. There's something else. And this nicely overlaps with conclusions by Virage with an independent approach. OK, so I will, I don't know how much time I have left. 2 minutes. OK, so I will end up with some future themes. So, of course, one of the, I think Sandro already mentioned this, one of the key things of JWST that it enables not only global studies but resolved studies of galaxies, just going beyond global properties, and combining stellar populations with morphology is a powerful way of trying to understand how things assemble. So this is an example of a paper led by Pablo in the CEERS collaboration. We're trying to do SCD fitting per pixel, and of course this is time-consuming. And if you could ideally, get the stellar populations of all pixels in JWST images. This takes time. So with Patricia, what we are building is, simulation-based inference a framework to recover star formation histories, again with neural networks, and we can get full posteriors of star formation histories in just very, very short times. And so what the plan now, so this is opening the route to try to get star formation histories for all pixels in JWST and link to morphology and better see how the different structural properties are assembling. And this is the next step that you can do with these kind of systems. And the nice thing is that you get full posteriors of the star formation histories and also uncertainties. All right. And I will end with a fun note because in this conference I always have to try to show some new machine learning stuff or what's happening in artificial intelligence. And what happened this year is that, is the boom of language models, large language models. And so I've been thinking how large language models can impact astronomy. And one way is, to try to have conversations about astrodata with a ChatGPT-like. So with a group of students a few weeks ago, we fed, galaxy images. We fine-tuned a large language model with galaxy images and text, skipping the details, but it's a multimodal model that takes at the same time text and images. And once it's trained, you can feed a galaxy image and ask questions about the image. And so this is a conversation that we had with this software that we call Lab Astro. And so you can ask, is the central galaxy edge-on or phase-on? And we'll reply, the image shows a galaxy with an edge-on orientation, which is OK. So it's looking at how many galaxies are there in this image, and do they exhibit something interesting? It says there are 3 galaxies in this image. 2 of them appear to be merging. I see 2. Maybe there are 3, but, or something in the background. But, it identifies something interesting there. Then you can ask, what is the dark feature in the central galaxy? It says the dark feature of the central galaxy could be a dust lane or a gas cloud. Without more information, it's difficult to determine its nature. So, it's not bad. It's been trained with conversations of astronomers. And so what this could be useful for, I don't know, but you can imagine feeding all figures and all plots that we have made as a community with descriptions of the figures. And then it can be a very, very powerful tool to train students and to understand data and explain what's in the data structure along with the descriptions of the figures. So I think there's lots of potential there. And I'll end up with a summary. I think I'm running out of time, so thank you very much.
Thank you, Marc. Questions for Marc? We'll take one over there and then Sandy.
In your figure, when you show the fraction of these galaxies, the function of redshift, at high redshift, the shape of the evolution with mass also changed. I was wondering if you think it's a physical thing or just a completeness at these high redshift, low masses.
You mean this thing here?
Yeah.
Yeah, that's a good point. I don't know. I haven't thought deeply about that. So, yeah, you say that, Yeah, I need to think. I don't know. I don't know if the completeness can do something like that. I don't know. That's a good point. I haven't investigated this in detail. Yeah, can look at that. Thanks.
The enemy of determining star formation histories with HST has been dust.
Right.
How will that figure into your plans for JWST data? At higher redshifts?
Yeah, that's a good point. So I think, what we are trying to is, include dust modeling, so in the forward modeling that you're using for training, but, it's always be dependent on the, on the dust model you have. It's degenerate, right? So our hope is that if we calibrate properly the uncertainties, which is this is the main point, the main goal of this, is that, you get full posterior distributions, you should be able to capture at least the degeneracies and make any conclusion, don't make overstatements because you have a full description of the degeneracies. That's the hope, but maybe I'm wrong. But happy to chat more about that.
Joanna, and then one quick question from David, and then we move on.
Thank you for that nice talk. I'm just wondering, for your model that you trained on TNG50 to classify the disks, did you also make sure that it was generalizable to, like, say, another simulation, just to make sure that your disk classification is generalizable?
Yeah, so that's the point I'm making here. So one thing that you see clearly here is that there's some. So the short answer is no. So we need to trace that, and this is something that we are looking at with Joel. But essentially, that you see clearly that there's a region here of the parameter space in which there are lots of TNG galaxies and there are no observations. So there's clearly a mismatch. So it's difficult to take any conclusions on that. So one conclusion that you can say is that the observed morphologies are not similar to the simulated ones. Now you can push this forward and try to get some physical properties on that, but this is just some speculation, I would say, at this point. And I agree that you need to have more simulations to try to figure it out. Yeah.
Thanks.
David?
Since disks are very interesting for this session, I remind the audience that bars are very powerful diagnostics of disks.
Right.
And in the past with HST, we just didn't have the redder wavelengths, and we did not have the resolution to really do a good job on that. So I think there's a lot of controversy whether they decreased or not. With your new and better data and machine learning, are you able to comment on at least what direction the bar situation is? Because it tells us things are flat. I mean, you don't get bars.
So I cannot comment that because we haven't done this statistically, but this is on the table. So we have the models now that think to get accurate bar fractions. So what we've done on CEERS for now is just selecting, cherry-picking some objects, and there are some examples of bars at redshift 5 or something like that. But we haven't done a systematic analysis. So this is, but it's a very good point, yeah.
So let's start Marc again. And our next speaker is Aaron. He's going to be talking about ultra-high redshift galaxies and comparison to galaxy formation.